So hello everyone, welcome to this another session at Vector Institute, research session at Vector Institute. My name is Shivam Kalra. I'm a PhD candidate at University of Waterloo. I'm also a research intern at Layer 60D. And it is my pleasure to host this seminar, which is titled Privacy in Machine Learning, Introduction to Differential Privacy. I'm delighted to introduce our speaker today, Dr. Jesse Cresswell. Jesse is the senior machine learning scientist at Layer 6 AI, TD, and he leads the risk division. He's interested in how healthcare and banking institutions can collaboratively build AI systems enabled by the private data sharing. He has completed his PhD in theoretical physics from University of Toronto as a Vanier scholar. So I welcome Jesse. Hi, Jesse. And without any further ado, we can start this talk.
Well, thank you, Shivam, for the nice introduction, and welcome to all of our colleagues from Vector Institute, my friends from Layer 6, and especially people coming in from the Kimia Lab at Waterloo. Welcome to you as well. I'll be talking today about differential privacy and how we can apply it to ML at a very high level. This will be an introductory talk. I don't expect that you've heard of differential privacy before, so we'll analyze this from the very ground up. But just a quick word first about Layer 6 and who we are. Layer 6 is the main machine learning research lab as part of TD Bank. So we're obviously working on machine learning in healthcare, in finance, but we're also very interested in healthcare and other aspects. We're a platinum sponsor of the Vector Institute, so we have many different active research collaborations with Vector and also with the MSCAC program at U of T. We're working on basically all major aspects of machine learning, CV, NLP, RL, and privacy as well. So if anyone's open to collaboration, please don't hesitate to reach out. We're always looking to meet new people. But let me start by reflecting on what we mean when we talk about privacy. Privacy is a term that constantly comes up in the public discourse, and everyone will agree that protecting privacy is a critical priority, especially in industries such as healthcare and banking, where we deal with sensitive information on individuals. But despite all the talk about privacy, I find that it's rarely defined in a rigorous way. Canada has many different laws about privacy and how we must protect personal information, the responsibilities we have as data analysts working in banking, for example, which is usually focused around protecting data that can identify individuals. But this type of definition may not capture the real spirit of what we mean by privacy in the context of data analysis. So in this talk, we want to explore if there's a rigorous way to define privacy, something that we as academics can grapple with and use specifically in the context of machine learning. So some quick examples that I've seen recently. For example, GitHub has announced the Copilot plugin, which lets you autocomplete code based on machine learning algorithms. But within a day of its release, people found that you could autocomplete large blocks of code that had been memorized from specific code bases. This is an example of the fast inverse square root algorithm that came from the Quake database, and it's completely reproduced from GitHub Copilot line by line, character by character. So we have to ask if this is private in any sense. If Copilot is learning about our code and able to reproduce it word for word, even if our repos are marked private, do we really have any sense of a privacy guarantee? Are we still comfortable uploading our code to GitHub, maybe our personal code, maybe our institution's code, if Copilot can see it and memorize it? Another example, just a random one, such as GANs, which are a generative model that try to generate images that are similar to things in the training set. Now with GANs, the generator that creates new images never sees the training data by itself. The generator just takes random noise as inputs and outputs new samples. It's the discriminator which sometimes sees real data and provides information to the generator through the loss function. But even though the generator never sees the training set, it may be possible for it to generate new images which are very similar to things that are seen in the data set. Can we provide any real guarantee that our generator won't memorize things from the data set and recreate it, potentially breaching the privacy of whatever data is in that training set? It's hard to say if there's any guarantee there that's possible. So as we embark on a journey to define what privacy actually means and how we can quantify it, let's use this nice framework where we have three parties interacting. First, there are subjects. Subjects are individual peoples who have the choice whether they not want to give up their data or not. They have a choice of whether they want their personal data to be used in some study or database. And they give that data potentially to the curator, who is a centralized party, one that's typically trusted, that collects that data, holds it, and creates a database from it. The third party are our analysts, or sometimes adversaries. They are people who want to analyze data for statistical reasons or to create studies and do research, or possibly for more nefarious deeds. We can't really assume that the analysts accessing our databases have purely good intentions. So what privacy is a promise from the curator to the subjects that no harm will come to them if they choose to include their data. Of course, with machine learning in mind, the more data we can collect and use, the better for the models we train. But we need to comfort the subjects that no harm will come to them if they choose to let us use their personal data. I'm sure most of us on this call have been in all three of these roles, certainly as a data subject, likely also as a curator collecting data, and more than likely also an analyst using data to produce some downstream tasks. So if we look a bit more at this promise, the curator is saying to the subjects that you will not be affected adversely or otherwise by allowing your data to be used in this database. The question then is how we can learn something as analysts or curators, how we can learn something about a population without learning details about individuals. Now, this is not too unfamiliar to machine learning scientists. We're constantly thinking about how our models can generalize outside of the training set. So how can we learn aspects of the population without memorizing too much about individuals there? To provide a broad example of what this promise means, let me give you an example of an individual who happens to be a smoker, and they're choosing to provide their data to some researchers who are studying smoking. As an outcome of this study, it's more than likely that the researchers will discover that smoking causes health problems. And as a result of that study, certain actions may be taken. It might be the case that health insurance companies see the results of this study and decide to raise premiums on people who smoke because it leads to health problems. It could also come about that our individual sees the results of the studies and realizes it's better for them if they choose to stop smoking. So clearly, the result of this study can lead to effects on the individual who chose to put their data in or not. But the distinction I want to make is that it's not the inclusion of one individual's data that led to those adverse effects. It was the outcome of the study as a whole. And that was likely to happen whether or not one individual chose to give their data. So in this scenario, even though effects did happen to the individual, the promise from the curator was not strictly broken. This is an important distinction to keep in mind as we dig into privacy more. What we're really concerned about is what can change when one individual chooses to add their data or not. Now, in the past, over decades, as people have matured in their thinking around privacy, many different approaches have been attempted to preserve the privacy of individuals. Probably the most common one is anonymization. This is what you'll see for compliance with legal and ethical regulations around protecting personal information. The curator in this scenario might choose to remove any personally identifiable information about a data set before publishing it. But this approach, in the end, doesn't preserve the promise. Despite it being used widely by banks and credit bureaus to exchange information about customers, or hospitals who might choose to release data for the use of research, maybe medical images or diagnoses, after stripping out personal information, anonymization by itself does not provide any meaningful privacy guarantee. It's susceptible to attack. Specifically, linkage attacks are a good example where outside information can be brought in to de-anonymize the data that we thought we had protected. There's many famous examples of this. One that was very high profile was with the Netflix prize competition for recommendation systems. In that scenario, Netflix released a large data set on how users had rated movies, which was very sparse. Certain users had only rated a few movies, or very rare movies were rated. So this was almost trivial to de-anonymize by comparing those sparse records with outside data sources. Specifically, IMDb also keeps track of movie ratings from individuals. And so when we see very uncommon combinations of ratings, it's easy to infer that the same individual did those ratings. So even though the Netflix data set had personal information stripped out, it was relatively easy to reintroduce that information. A second attempt that has been used in the past is where the curator will not simply release a database entirely, but keep it to themselves and instead answer queries that come from data analysts in order to help them do their job. But of course, we can't just let any query through. The data analyst could query something very specific about one individual person. And if we let that query go through, it will clearly compromise the privacy of that individual. So to avoid those effects on individuals, what has been tried is to answer queries that are only on large enough groups of the population, maybe hundreds or thousands, so that it's not specifically information about one person. But this still doesn't hold up to any scrutiny when it comes to privacy. It's also susceptible to attacks, in this case, a differencing attack. So if we know that an individual is in the database, we can make up two different queries, which are individually over very large sets of people. But when we take them together, we can reconstruct information about specific people. For instance, if it's a medical database, I can have my first query as how many people in the database have disease Y? And as my second query, how many people not named person X have disease Y? Based on the outcomes of those queries, I will either get the same result both times, or I'll get slightly different results. And comparing them, I know exactly if person X has disease Y or not. A more modern approach is called federated learning. It's a distributed machine learning approach where we avoid centralizing data on one server. Instead, we try to train machine learning models on the device where the data is collected. Usually that's going to be a smartphone. The device does our calculations for us, such as our gradient updates, and those gradients get sent back to the centralized server where they can be aggregated together for improving the centralized model. Now, I will say federated learning is not primarily a privacy approach. It's more so about training machine learning models in a way that's communication efficient when we have an enormous amount of data. But if you look at the original papers on federated learning, they do use privacy as one motivation. And intuitively, it might seem like federated learning is more private because personal data never leaves a personal device. It never goes back to the centralized server. But with any scrutiny, we can say that federated learning does not provide any privacy guarantee. We know that neural networks have the capacity to memorize individual training examples. So even if I do a gradient update on my personal device and I send that back, the gradient update might contain exact information about my personal data. So there's no guarantee that my information won't be compromised in this scheme. So these are three approaches that have been tried, and they don't seem to reach our promise from the curator. If you go to the extreme, you could even say that privacy should mean that nothing can be learned about an individual when data is released. That would be the ultimate guarantee we could provide. But it's completely useless in practice. If we can't learn anything about anyone in the database, then there's no information to be gained at all. Even if we're learning very general information, we're still learning something about individuals. Let me give you another example. If it's a database on chest x-rays and we're trying to determine if someone has lung cancer, maybe we learn the general information that 3% of people in the population have lung cancer. That is still information about the individual. What we know now is every individual in this database belongs to a population where the prevalence of lung cancer is 3%. Maybe that's not very useful information, but it is some information about individual. So it just goes to show that there's a fundamental trade-off here. If we want to learn anything about data, if we want to learn anything from data analysis, that necessitates we learn something about the underlying data, about the individuals in that data set. So privacy is not a binary concept. Instead, we should think about privacy as a resource. It's something that is used up as we gain more and more information from a database. And that's okay. It's okay to use up some privacy if we're gaining useful information that we can use to do our research. But what we want to do, again, as academics and researchers, is provide a formal definition, a formal framework where we can quantify privacy as a resource and quantify how much privacy is being used up as we are extracting information. So differential privacy is a framework that allows us to formally define privacy as a resource and grapple with how it is used. To motivate differential privacy, I need to introduce one more thing, and it's the concept of randomization in response to queries. Let's imagine you are a social scientist doing some research on tax fraud. If you come up with a survey about tax fraud and you go out to ask people, have you committed tax fraud? You're not very likely to get truthful answers from people who have committed tax fraud. Nobody would want to admit to that on your survey and risk incriminating themselves. How do they know you're not the police and going to throw them in jail after admitting tax fraud, after all? So what people have done in the past is to design surveys with an element of randomness in them. So what you do is ask a subject before answering the questions on the survey, in secret, flip a coin. Only you can know the answer, the heads or tails answer from that coin. And if it comes up heads, don't tell anyone, but answer the questions truthfully. If it comes up tails, flip a coin again in secret and just answer randomly. If it's heads, answer yes. If it's tails, answer no. Doesn't matter what your truthful answer actually is. So in this way, each person participating in the survey has plausible deniability. If the results of the survey are leaked and we find, oh, you just admitted to committing tax fraud, well, the individual can say, no, I didn't actually commit tax fraud. I just did the coin flip thing. It instructed me to answer yes, but I didn't commit tax fraud. And so they feel secure in following the instructions and that they won't be sent to jail for participating in the survey. But nevertheless, even though the results are somewhat randomized, we get useful information because we understand how those results were generated. For example, if 100% of the participants actually had committed tax fraud, you would still expect 25% of them to say no and 75% of them to say yes based on this coin flip scheme. And on the other extreme, if nobody committed tax fraud, 25% of them would probably say yes on the survey. But the analyst, by understanding how the data is generated and the random process behind it, can still get useful estimates of the prevalence of tax fraud in this case. But it's randomness in response to these queries that is key to solving the issues we discussed above. This system of collecting data actually does provide a privacy guarantee through plausible deniability, but it's only because of the randomness that was interwoven. So this is our first step to defining differential privacy. It works on the basis of randomized mechanisms. A mechanism is just another word for a query. It's something that, it's a question we're going to ask to a database and hope to get an answer back. But unlike the typical queries that we would be used to in SQL or whatever else, these mechanisms will not be deterministic. They'll not always give you the exact truthful answer. There'll be some probability that it gives you various different answers. So a randomized mechanism is something that is a function that takes a database and returns an answer with some probability. There's some probability for each possible outcome. Now, I've been talking about databases a lot. I haven't been rigorous. So as we move to a more formal definition, we should clarify what a database means. We can think of a database just as a collection of rows where each row contains information on one subject, one person. We also think of each row as a unique entity. If you change any one bit of information in that row, you're completely changing the identity of that row. So this allows us to meaningfully talk about how similar two databases are. We can define a distance between databases like a Hamming distance, which is just the number of rows you would need to change in order to go from one database to the next. So if I write that down mathematically, I can take X and Y to be two different databases, and XI and YI are indexed rows in that database. The difference XI minus YI will be 0 if those rows are exactly the same, and it'll be 1 if they're different in any way. So I just sum up those differences to get the Hamming distance or the L1 distance. So now with those elements, we can actually proceed to talk about differential privacy and define what this framework is. It's a bit formal, but let's consider two databases, D and D prime, which only differ by one record. They're adjacent. They have a distance of 1. Also, let's consider a randomized mechanism M, which acts on those databases D and outputs some result. Not deterministically, but it will stochastically output some result. We say that such a mechanism is differentially private if the results of the mechanism are almost indistinguishable for all possible adjacent databases. That's the high-level description. More formally, we would say, in mathematical terms, a mechanism is epsilon delta differentially private if for all subsets of the possible outputs and for all possible pairs of adjacent databases, the following inequality holds. This says that the probability that the mechanism acting on database D gives us a result in the set S must be less than or equal to the probability that M acts on D prime and gives us a result in S, multiplied by some multiplicative factor e to the power epsilon, and with an additive constant delta. So I understand if that's a lot to take in at once. It is a pretty formal definition, and you should expect that it takes some time to grapple with it and internalize what it means. But let's try to explore it a little bit and break down what's happening here. I often find that building intuition it helps to look at counterexamples. So let me give you a mechanism which is not differentially private. That mechanism is one that returns the exact count of rows that satisfy a property P. That's something that's very useful to us as data analysts. But consider that we can find neighboring databases where the probabilities of outcomes are very distinct. For example, if I take a database with n rows that satisfy property P and I add one more row with the same property. Well, the probability that the mechanism acting on D gives the answer N is 1. It's always going to return 1, or it's always going to return N because it's deterministic. So the probability is 1. But when the mechanism acts on my modified database, it will never return N. It will always return N plus 1. So the probability of getting N is 0. Those probabilities are extremely distinct. And we know that this mechanism would compromise the privacy of individuals. Thinking back to the differencing attack, if we get exact counts from our database, we can infer exact information about individuals. So there's no sense of privacy. But this count mechanism can never satisfy the inequality because the probabilities are so different. Unless we let epsilon go to infinity, which means we really don't have a guarantee, or we let delta be equal to 1, again, we really don't have a guarantee. So what this counterexample shows is, one, that any differentially private mechanism must be randomized. The example I just gave is a deterministic mechanism. You can think about it a little bit and convince yourself that any other deterministic mechanism will suffer the same problem on adjacent databases. So it's randomness that allows us to cover up the differences between two adjacent databases. But also we see that this is a quantitative definition. We have two parameters, epsilon and delta, which control how much privacy is preserved or guaranteed. Epsilon must be something smaller than infinity to provide a meaningful bound, and delta must be some number smaller than 1 for it to be meaningful at all. But also, if we lower both epsilon and delta, we're certainly going to get better privacy. Then the probabilities of any outcome on adjacent databases will be more and more similar. And so we'll have less ability to distinguish information about individuals. That's exactly what we want. The last thing I'll point out is that differential privacy works on the worst cases. In this definition, we're not assuming anything about typical outputs or common outputs. We're not assuming anything about databases that we're likely to encounter in practice. We're talking about the worst possible cases, potentially, very rare outputs, databases that are highly unlikely. But this guarantee still needs to hold for all possibilities. It's extremely strong in that sense. Let's now review the promise from the curator, who said that you will not be affected adversely or otherwise. Does differential privacy hold up to this promise? Well, yes. If we are to add one subject's data to the database, differential privacy guarantees that the likelihoods of results from these mechanisms can only change by a small factor, e to the power epsilon, or the additive factor delta. So as long as the curator can provide guarantees that epsilon and delta are small, they can provide guarantee to the subjects that they will not be affected with high probability. Going beyond the definition, differential privacy provides a number of different properties which are extremely useful as we look to applying it in machine learning. First of all, we saw the problem with linkage attacks, that if an attacker can bring in outside information, they might be able to compromise the privacy guarantee. So the question is, with differential privacy, is it still vulnerable to people bringing in outside information? Well, now that we've developed a rigorous mathematical framework, we can actually study that question and answer it concretely. No, differentially private mechanisms are completely immune to any outside information or any post-processing. No matter what you do, no matter what information you bring in from the outside, as long as it doesn't involve the private database itself, you cannot weaken the epsilon delta guarantee from a differential private mechanism. Differential privacy also jives with our notion of privacy as a resource, and that privacy gets used up the more and more we access a database. Specifically, the epsilon delta differentially private mechanisms quantify how much privacy is being used up as we apply the mechanisms and as we compose them over and over. For one example, if we were to apply the same mechanism k times, you could think of the whole thing as a single large mechanism, and analysis shows that the large mechanism will provide a DP guarantee, which is with k times epsilon and k times delta. So in other words, as we compose a mechanism many times, the epsilons and deltas add up. We have a very straightforward way to analyze privacy as it's being consumed in a longer process. So in practice, differential privacy allows the curator to make this promise to the subject, but it will only be useful if analysts can still extract useful information from databases. So what we're thinking about now is a curator holding a database and allowing queries that come from differentially private mechanisms. But that leaves the question, how do we design differentially private mechanisms that are still useful, that still give us usable results as analysts? Some of the things that we'd like to do come from deterministic queries that we're used to. Things like counting the number of rows with a property or summing their values or taking averages. None of these things preserve privacy because they're all deterministic. And we saw an example of that. So how do we bridge the gap between these useful queries that are deterministic and differentially private mechanisms? One thing that we can do is take any deterministic query and add random noise to its output. And that produces something which is potentially differentially private. So this is our first example of a differentially private mechanism. It's also called the Laplace mechanism. What we do is take a deterministic query denoted by F acting on the database, and we add noise to its result, which is noise drawn from a Laplace distribution. And just to remind you, a Laplace distribution, well, it's a family of distributions which are like two-sided exponentials. They have two parameters, so there's a mean parameter. Usually we'll just take it to be mean of 0, as shown in this diagram, but also a width parameter. So as the width b is increased, the Laplace distribution is going to be less peaked and wider. So as it turns out, this Laplace mechanism, where we take a deterministic query and add noise to the result, is differentially private. It satisfies the inequality for differential privacy with particular values of epsilon and delta. Turns out that delta is equal to 0 in this case, which is the best possible. And epsilon is the ratio of delta F to B. Now, what's delta F? Well, delta F is the sensitivity of a function. It's the maximum difference between the result of the query F on two neighboring databases. So this epsilon guarantee does depend on what function F we're talking about. So let's come back to the example we've been working with. On a counting query, if we were to change the database by one row, what is the maximum amount that the count can change by? Of course, it's 1. If we add one row, the count will either change by 0 or by 1. So the sensitivity of that counting function is exactly 1. And intuitively, if you can only change the result of the query by 1, if you add a new row, then you can cover up that change, or you can obscure that change by adding a little bit of noise. If you added noise that was around 0.5 or 1, you wouldn't be able to distinguish the outcome of the query if it was on the original database or the modified one, based on the noise. But as a different example, let's think of the sum query. So where you sum all the values of a column in the database. What's the sensitivity of that? Well, it's unbounded. If I add one row, I can set the value of that row to be, well, any number I want. It could be exceedingly large, and that would have a great effect on the sum overall. So the sensitivity of the sum function is unbounded. And from the intuitive sense with privacy, If I see the sum changes by a wild amount on adjacent databases, I can certainly infer something about the row that was added. So the privacy guarantee given by the Laplace mechanism is proportional to the sensitivity. The less sensitive, the more strict privacy bound we get, and inversely proportional to the amount of noise that we add. Adding more noise covers up the differences and provides a stronger epsilon guarantee. So this is a very useful mechanism, and we can now think about applying these ideas to machine learning. But generally speaking, machine learning poses a number of different challenges from the privacy perspective. We've already talked about how neural networks can often memorize individual training examples. And certainly if we're doing that, we're not protecting the privacy of individuals. The second problem is that we often need to access the database numerous times in order to train a model. How many epochs does it take to train a large-scale neural network? Each epoch, we're accessing everything in the database at least one time. Lastly, well, one other example, there's many others, but once we have trained a model, we will typically want to use it for inference over and over again, many, many times. If we're thinking of privacy as a resource, it might be that running inference is using up some privacy, or accessing the database during training is using up some privacy. So these repeated steps are going to be consuming potentially too much of our privacy budget. So what we can do in machine learning is think about a number of distinct steps in the training and inference pipeline where we might inject a privacy guarantee. So for example, we might be able to train our model in a way that respects the privacy of the database. So point one, we can provide a privacy guarantee between the data and the model. For instance, if the model is accessing information in the database, we might be able to add noise to what's coming out of the database to provide a privacy guarantee like the Laplace mechanism. Or we might be able to limit the number of accesses that the model has to the database. And in that way, the resulting model respects privacy, and we can do anything we want after that. But you could also consider adding a privacy guarantee at a different stage, such as after the model's trained. Point two, train your model in whatever way you like with unlimited access to the database. But now you can treat your model in a way that preserves privacy after the fact. For instance, take your large teacher model and distill it into a student model in a way that respects differential privacy. So at the end, you have a teacher model, which is not private at all, could have memorized everything in the training set, and you have a student model, which respects privacy. You can then use that student model all you like. A third place that you could try to inject privacy is after you have a trained model and during the inference step. So you could, of course, limit the number of times that the model is allowed to perform inference and say that each time it performs inference, it uses some privacy, but we'll cap it at our privacy budget. Or you could even add noise to the outputs of the model in the essence of the Laplace mechanism again. So for instance, if we have a downstream task like classifying images, the model will output some probabilities, maybe some logits over the classes, and we can add noise to those probabilities before revealing what the predictions were. And so hopefully most of the time the noise won't overcome the fact that it's confident we have a cat here. But on occasion, the noise will happen to push dog above, and we'll just have to deal with that. So to be more concrete, let me zoom in on one of these instances and how we can, in more detail, train a model in a differentially private manner. So let's take point one, where the privacy guarantee is between the model and the database itself. One method that's been used is called DP-SGD, or differentially private stochastic gradient descent. The idea here is to control the gradient updates that the model sees during training and provide a privacy guarantee that way. Now, thinking back to our Laplace mechanism, gradients are like a query. We select some data from the database, we run it through the model, do backprop, and we get deterministic gradients out of that. But in principle, if you change one element of the training set, the resulting gradients you get can completely change. In other words, the gradient query has unbounded sensitivity. So according to the Laplace mechanism, we need to have a finite sensitivity in order to have a finite differential privacy bound. So what we can do is clip the gradients. We fix an upper bound on the norm of the gradients, and if we get a gradient back that's too large, we clip it down to the upper bound. Then we'll have a clipped gradient query with finite bounded sensitivity. And so we can apply our Laplace mechanism or similar and add noise to that result. So now we have clipped noised gradients, and we can use those gradients to take SGD steps and train our model in this manner. Now, you're probably familiar with gradient clipping and even adding noise to gradients as somewhat standard things to do in machine learning. They're both feasible regularization techniques. As it turns out, using both of those regularization techniques together gives us a meaningful privacy bound. So all we have to do is track how many times we are querying the database, getting those clipped noise gradients, and use our composition ideas to add up the epsilon delta guarantees over all the queries. But the benefit of this is once the model is trained on the other end, we can do anything we want with it, and we'll preserve the same amount of privacy because of the post-processing guarantee. Since this is an introductory talk, I'm not going to get too much into the weeds, but to pique your interest, hopefully, there's many other avenues that you'll like to explore in order to start using privacy in machine learning models. For instance, I talked about composition theorems today and how epsilons and deltas can add up linearly, but people have been able to do better by analyzing theoretically the situation. Analysis can provide us with sublinear composition guarantees. And this can be extremely important for machine learning where, as you've seen, we might want to do this gradient query many, many times over the course of training. If we had a linear growth in privacy use, it might not be sufficient. But sublinear growth provides us the ability to train for a much longer time and achieve more useful models with relatively lower privacy budgets. This is related to the second point on privacy accountants. These are methods for tracking how much privacy is being used during model training and providing very strong bounds on the actual amount of privacy that's being used up. Third on my list is various relaxations of differential privacy. So the definition I presented today in terms of epsilon and delta is very, very strict. It's probably the most strict you can get. We're talking about the worst case in all scenarios. But you can consider weakening that definition, consider something else that might maintain some or many of the desirable properties that differential privacy has while being a bit more amenable, maybe easier to use in practice. So there's various relaxations which have proven to be very useful. And last, we can look at interesting mechanism designs. So the DP-SGD mechanism I talked about can be widely used in almost any machine learning algorithm that relies on SGD. But it might be that in your specific application, there are different ways of applying privacy guarantees, maybe at point 1, 2, or 3, as I outlined, that provide you a better guarantee. For instance, I mentioned knowledge distillation. You can consider using DP-SGD for knowledge distillation, of course, but you can also try to come up with more advanced techniques for distilling the knowledge from a teacher in a differential private manner. So I hope that gets you interested to look more into differential privacy and how it applies to ML. in conclusion, some of the things we've looked at today is how we can never hope to have perfect privacy for every individual while still getting some meaningful information out. We've also seen that randomizing our results is essential for protecting privacy and meeting the strict requirements of differential privacy. But also we've seen that privacy should be thought of as a resource. It's something we can use up as long as we track how much we're using and limit how much we're using. It's differential privacy that allows us to quantify privacy as a resource and provide that guarantee to our users. We'll never exceed an epsilon delta breach of your privacy. Our job as scientists now working in the field is to develop new mechanisms and applications that will minimize the privacy use so that we can provide the strongest guarantees to our subjects while still maximizing the utility and accuracy of the results that we get. So I find this to be a very interesting confluence of techniques interacting with machine learning. And if you also find it interesting, I hope you'll look into some of these resources on your own. These are things that I've used to learn about differential privacy, and much of it is what went into the slides today. If you like learning from a textbook, you can look at Dwork and Roth. If you want a more quick overview, including things we talked about today, our friends over at Borealis AI have written several blog posts on this matter. Or if you are a student and more akin to taking a university course, Gautam, who was in the chat earlier, has been very generous and made his Waterloo course available on YouTube, so you can watch his lectures there. Just to conclude, I'd like to thank you for all your time and attention. I'll be happy to answer your questions now. And if you're at all interested in working on differential privacy, we at Layer 6 are more than happy and we're always open to new collaborations. So let me hand it back over to you, Shivam. Thank you once again for your attention.
Thank you, Jesse. That was a great talk. And in fact, my lab, Chemia lab at University of Waterloo, we work a lot with histopathology data and also the medical images. And especially in these fields, the privacy of patient data is very critical. So especially for us, this was a very informative talk. So thanks a lot. And so it's a time for question and answers. I would like to ask our listeners and audience to ask any question to Jesse. You can also ask your questions in chat, or you can just unmute your mic and ask your questions. I guess we'll wait, but could I ask you the question, Jesse?
Of course, you can ask the first question.
So obviously, when you are adding the privacy to a model, you have to make this process randomized, like you said, random mechanism. Is there a way you can quantify how much a model would be hurt by adding these random noises?
Yeah, as I mentioned, both clipping gradients or adding noise are common regularization techniques. So on their own, they don't necessarily hurt performance. And some examples, they can actually improve generalizability. But there have been studies on applying the combination of the two and how that affects the utility of our models. It turns out that applying both of those techniques at once tends to be too strong of a regularization, and it will negatively impact performance. So we can compare training a model with no privacy guarantee, just using as much of the resource as we like, or compare using differentially private techniques and see how the model performance differs on those two. So in general, there is some decrease in performance when we provide these privacy guarantees, but it may be the case in banking or healthcare that you work in, Shivam, that we don't have a choice. We must protect privacy. So we need to work the best we can to improve the utilities of our model in that case.
Sure, thank you. We have another question. So Alan is asking, how can a differentially privacy differential privacy be applied to a computer vision problems where data sets includes video, photo data? That is, you cannot blur the faces.
Well, I don't know if we should say off the bat that we cannot blur the faces. We can consider working on image data. It's a very common application. And you can consider adding noise to those data samples. I don't know if that would be the most effective technique, but you can consider injecting a privacy guarantee at different points in the pipeline. Maybe you want to train your model on video or photo data without any restrictions, but then add noise to the predictions from your model. You can still get a differential private guarantee on how much privacy you're preserving for the people who contributed their images to the data set by applying differential privacy to the outputs. You don't necessarily have to change the inputs.
I guess just to extend that question further, let's say you are a lab, you have released a model already, and now you realize that you might have leaked some information through that model, like implicitly.
Yeah.
How can you now change the model to make it more private?
If you've already released the model, well, maybe all bets are off. But if you want to revise what you're doing, you might consider applying something like DP-SGD as you're training the model and tracking the privacy that's used up in that process. So in that case, you don't do anything like blurring the faces or adding noise to the medical images, but when you feed images through your model and it produces gradients, you can add noise to those gradients before updating your model. So that can help to obscure any fine-grained information about specific examples. The aim here is to learn general properties about the data set without learning specifics about individuals. So adding that noise can obscure the individuals.
So yeah, I think for our fields like banks and medical fields, like this should be made compulsory to post privacy bounds for your model or data that you're releasing.
Yeah, I don't think it's been thought about too deeply in the traditional settings of healthcare and banking. I know from working in a bank that we are communicating personal or customer information with credit bureaus and then receiving back anonymized information from other institutions. And in truth, as I outlined, anonymization is not really sufficient to guarantee privacy for individuals. So what I would really like to see is a setting where banks can communicate with one another directly in a differentially private manner that provides a real strong guarantee to their customers while still getting utility of information from different sources. And I think the same applies in healthcare, where we have many hospitals with an obligation to protect individual patients, but certainly where they could benefit from sharing data more freely.
If I could ask you maybe insider question, if you would be willing to answer, but how does TD handles the information, the customer information? Do they apply differentially private mechanisms on it, or how's it been handled?
So internally, we don't apply differential private mechanisms to our customer data. We have permission to collect data on our customers. That's something that customers agree to when they come to a bank. Any bank is not just TD. But we have an obligation to protect that data. We can't simply release it for public use. We have to ensure that only responsible parties, relevant employees are able to access that data. So this is a setting where the data analysts are insiders, they're curators too. Even in the setting that I outlined, the curators have to be a trusted centralized party. The subjects are trusting their personal information to the centralized party. It's just that we don't want to reveal it to outside analysts.
Sure. Any other questions? I think it's already 5 o'clock, so we could wrap up this talk. So thanks a lot, Jesse, for all your time, and I appreciate the audience as well for listening this talk. So thanks everyone, and have a wonderful evening.
And thank you to you, Shivam, for hosting.
Thank you.
Thanks. Bye.